We're now going to turn our attention to yet another concurrency pattern. This is really more of a synchronization pattern. And this is a pattern that's called the thread-specific storage pattern. And this pattern also appears in the POSIT 2 book and is documented, of course, also in a paper on my website, which I'll provide a link to later. So let's start by talking about the context. As we've mentioned a couple of times, but really haven't looked at in detail, Android only allows one looper per thread. So if you're going to be using loopers, we've seen examples of loopers like the user interface thread or just a looper thread in general, or handler thread in general, then there's going to be one looper that's used to process all the messages that are passed to that thread by the message queue. The problem with having just one of these things, if you're not careful, if you do sort of the naive approach, you could have a looper registry. That could become a multi-threaded bottleneck in a multi-threaded process, because you'd have locks all over the place and you'd have to basically go look up in the registry, and you'd have to find the looper for that thread using some kind of ID, a thread ID, and it would just get to be unwieldy and inefficient. Why would that be the case? Because of course you'd have to have synchronization required using various synchronized methods like synchronized keywords or the Rancher lock and so on. So a better approach for situations where you need one of something per thread is often to apply something called the thread-specific storage pattern. And this allows multiple threads to use a logically global access point. So it looks like it's global from a programming point of view, but in fact, it's actually implemented in a thread-specific way. So you can access, in this case, the one and only looper that's actually local to the thread. And as you'll see, the nice thing about this is using Java thread local, which is the Java way to implement the thread-specific storage pattern, doesn't incur locking overhead on each access to the object because it's nestled away inside the internal state of the thread. So it's very efficient. So what's the intent of this pattern? The intent is to allow multiple threads to use one logically global access point to retrieve an object that's actually stored locally to the thread without having to incur locking overhead on each object's access. So every time you access the object, you don't actually have to grab a lock. You can just go and get the thread local or thread specific instance. But the way it's treated, the way it feels, is it's as though you're getting access to a global variable, but it's actually local to the thread. Now, as we'll see, this requires a little magic to make it work efficiently. So let's talk about this pattern. So you would apply this pattern if you want a concurrent program to be both easy to program and efficient. And the reason behind this is you want to be able to get access to objects that are logically, or rather physically local to make them efficient, but appear global, so they're easy to program. That's the idea here. One other motivation for this pattern that is actually very common in practice, and we'll talk about that when we get to the applicability part, or when we get to the known uses part in a minute. You may need to take legacy code and retrofit it to be thread safe. And a lot of legacy code, especially old code going back decades, was not designed with multi-threading in mind. So there'll be references to certain state, for example, like the Aeronaut error value, where if you wrote your code to use single threading way back in the day, you'd use Aeronaut, we'll talk more about Aeronaut, as a way to find out why some call failed. When you start running in multi-threaded environments, Aeronaut becomes a problem. And so you'd like to have some magic way to make what looked like a global variable become a thread local variable instead. And we'll talk about Aeronaut later and how it gets used in that way. But before we do that, let's talk first about the structure and the participants that are in the thread-specific storage pattern. So one thing we're going to have is what we call the thread-specific object proxy. And this is just intended to make the whole thing look like you're making a method call on a global variable. So it doesn't look any different from writing normal code. But in fact, under the hood, it's going to do some magic to make the actual method call be resolved in the context of a thread local object. So in the context of the pattern we're talking about here, the Java thread local class would be a good example of the thread-specific object proxy. There's something called a key factory that's used to make the underlying keys, which are used to identify how things work. That's also kind of handled by the thread local class in Java. There's something called the thread-specific object set, which is going to have this mapping from keys to local objects. And that's used in the context of Java by something called thread local values, which is going to basically be a special container or collection that keeps track of these mappings. And then the thread-specific object set maintains a mapping to the underlying thread-specific objects, which are going to be local to each thread. In our particular example, that's going to be the looper that we're going to have in the context of Android. So some of the stuff we're talking about here comes right out of Java, like thread local and thread local values. Other things here are coming out of the context of Android, like the looper. Let's take a quick look and see how this thing gets used in practice. So what will happen is an application will invoke a method on a proxy, and that is then going to be resolved. That's going to be resolved into the thread-specific object set, which will take the particular implementation out of thread-specific storage, which actually gets implemented by the underlying threading mechanisms when all is said and done. And then that would then be used to identify the specific thread local object to forward the call to delegate the processing to. So all the processing is done by a thread local object, which means that there's no locking overhead because there's no contention from other threads. So once you get this, you're going to get the underlying thread-specific object, and then that gets forwarded to the thread-specific object that's stored in a way that's going to be very efficient and requires no locking. So as always, what are the pros and cons of using this approach? Well, one thing is that it's very efficient relative to sharing objects within some kind of concurrent or synchronized container. So for example, if you take a look at the code here, which comes out of the Java util concurrent package, the thread local class, as you can see, makes invocations in such a way that there is no locking. So we're able to get things out of thread-specific storage, and we're able to update the state in a way that will not incur any locks at all at runtime. When you wrap this thing properly with the appropriate wrapper facades and proxies, as the pattern dictates, then it just looks like you're making a method call, but underneath the hood, it's all being handled appropriately and getting access to things that are thread local. So again, very clear, very clean. This is actually some of the code that you see if you look at the looper implementation in Android. We'll take a look at that in more detail in the next video. But basically what we're doing is we're making ourselves a thread local object, and then that gets initialized in the prepare hook. And so we're only allowing one object within the looper, and we check to see if it's already been set. We throw an exception if we're trying to have more than one looper in a thread. Some of the nice consequences here is we can make the code be very reusable and very portable. And that's because we can provide wrapper facades, which is yet another pattern from the Post-it2 book documented in the link below, that can shield the underlying differences, or it can shield the application code or service code from the underlying operating system details. That, of course, is kind of what Java does for you just by virtue of the fact that it's meant to be write once, run anywhere. But you could also see other frameworks like the ACE framework, ACE toolkit that I've developed over the years, which allows you to encapsulate either C++ or C code to basically shield you from the differences between different operating system APIs, like Windows versus Linux versus Solaris versus VxWorks, and so on. So the downside is that this particular pattern encourages the use of global objects, which have their own headaches. And so, you may have some problems with that. Not everything requires this transparent thread local access. For example, the Android async task approach basically just uses fields to keep track of these differences. So it hides all that stuff from you. It doesn't require thread-specific storage. The other problem, whenever you start using globals, even though the implementation is not global, the logical properties are global, is it tends to obscure the structure of the system, which makes it harder to understand because the relationships between the components are not clear. once you understand the thread-specific storage pattern, using the thread local class in Java is pretty straightforward. But until you understand the pattern, it's rather perplexing and vexing what this class even is supposed to be doing for you. Also, if you don't implement things properly, then you can actually have a fair amount of overhead. Naturally, Java does a good job of making things efficient, but that's not guaranteed. So what are some good examples of this pattern? The Aeronaut macro in multi-threaded implementations of standard C is a classic example of this. And if you use Aeronaut, you can make a system call or a system function call. And when it comes back with a failure result like -1, you can use Aeronaut to find out what happened. And the way it typically works in practice is that Aeronaut is actually defined as a macro that ends up accessing thread-specific storage. And that's because legacy code used Aeronaut as a global variable. And then when people retrofit multi-threading on top of classic single-threaded POSIX code or Unix code and so on, they needed to find a way to transparently make it work in a thread-safe way. And so you can read more about Aeronaut here and learn more about how it works. This is actually the implementation of Aeronaut you might find on a classic version of Linux or a classic version of Unix or Solaris and so on. And it actually uses another pattern that we've talked about before called the double-checked locking optimization pattern. And in fact, that's actually where I first stumbled upon the concept of double-checked locking when I was writing the paper back in the day, was how it's implemented internally to implement the Aeronaut macro in modern versions of C that require multi-threaded access. We provide a real nice template in my ACE toolkit called ACE TSS for ACE thread-specific storage. And it essentially uses C++ parameterized types to encapsulate all the details. You can read more about that in the posted to book or in the link below. The magic secret sauce with the ACE TSS template is it uses C++ delegation, which is the operator arrow method, to provide thread-specific smart pointers. And it's really clever, really cool. Won't go into it now because it's a little outside the scope of the course we're talking about Java, but if you want to learn more about it, take a look at the paper or just look at the source code. It's very clever. Okay, so there's also, of course, lots of user interface frameworks that use this pattern too. Android, Windows, probably just about anything that wants to have separate threads will use this one way or another to keep things working with loopers. So to wrap up, thread-specific storage eliminates the need for locking when you access data that is inherently thread-specific, and it simplifies legacy code because you don't have to pass parameters everywhere, so you just make method calls or use macros, and you can access things that look global but in fact are implemented in a thread-specific way. The downside, of course, with that is it encourages people to use global objects, at least logically global objects. They're not physically global, but they look global. And that leads to some problems with respect to tight coupling and dependencies and so on and so forth. So that wraps up the overview of this pattern. We'll come back and look at it in more detail when we talk about the implementation in Java and Android in the next part of this lesson.